Alrighty, guys. As promised, we're going to, I'm going to go ahead and post this video for the second fundamental theorem of calculus and link with it, the assignment that I gave you when we chatted yesterday. And I will also upload the answer key to those as well as, other information that's relevant. After our discussion, one of y'all actually messaged me and asked why you were doing this. That person said that they understood the procedure, but they didn't understand why they were doing it. Now, there are two different why questions, actually, that I could identify. The first of them is why have a function defined as an integral. Okay, so basically the question is, why do we even have something like this going on where there is a function defined as an integral? Well, if you can have a function that's defined as a rate, so basically a velocity function, will be a function, but it will also be a description of a position function. It'll describe that position's rate of change. You can have a function defined as not a rate, but an accumulation, right? How fast is something accumulating, okay? The second question that I could discern is, why must I do, or basically learn how to do, why must I do the derivative of g by this method? Okay, and that means, if I can figure out a way to basically get to g prime without doing the plugging in and making it, f of x, then I should just go ahead and do it. Now I'm going to answer each one of these in turn. Well, I've already kind of answered this first one, but I'll do it a little more fully, okay? Now, why have a function defined as an integral? Okay, well, sometimes I'm given a scenario where I'm not given the position function, right? I'm not given the position function. Instead, I am given the velocity function. And if I were to graph a velocity function, I would, time here, right? And then the rate, or the velocity, v of t, on the vertical axis, okay? Now, notice that this right here, like I said, this measurement on the vertical is rate, and this is time. Let's say that I have a constant rate over time for this amount of time. What is rate times time? Rate times time is distance. Okay? So that's just one example of how getting the area under a curve actually gives you something useful, right? So if you're given the velocity function, you basically accumulate or integrate the velocity function over time, your answer will be distance. Now that's true if the velocity function is constant. That's also true if the velocity function is variable. Even if the velocity function is variable, it's still rate times time, and of course the integral will split that up into an infinite number of infinitesimally thin cross sections and accumulate it from A to B. Okay, so basically sometimes you will be given a function, whose accumulation over time is something that is sought after, okay? So that should explain why sometimes we'll have a function that is defined as an integral, a function that is defined as the accumulation of another function. Now the next question is, why must I do the derivative by this method, right? Because I've already shown you how, if I have a function from a to x of f of t dt, I know that basically by the first fundamental theorem of calculus, that this right here, this integral, implies this difference. Okay, well, that's all well and good if you are actually capable of integrating this. Now, if I'm given, g of x is equal, 1 to x of cosine x or cosine t dt, then I know that I actually can say, well, that's basically the antiderivative of cosine is sine x from 1 to x, and that becomes sine x minus sine of 1. So g of x is equal to sine x minus sine of 1. Sine of 1 is obviously a constant, and so I can take the derivative and just get cosine x. And I can actually take the integral, get a representation of it, get an analytic representation of it, and then take the derivative. The problem is, and I've mentioned this before, some integrals cannot be taken. Or at least there are a lot of them that can't be taken with the skills that you presently have, okay? So let's say we have, e to the, let's say we have e to the t times cosine t dt. Okay, well, I'll give you a challenge. Go ahead and see if you can actually integrate that in order to get it into an analytic representation, which you can then take the derivative of. That's going to be really, really tough. What we actually need is we need a process by which we can go ahead and skip this elusive step over here where we're invoking the knowledge that this equals an implied difference and just skip straight down to the derivative. And in this case, it's just e to the x cosine x. Okay? Now, simply because you may not be able to arrive at this difference doesn't necessarily mean that you need to put out of your head that this integral does indeed imply that difference, because the implication of that difference is going to be important when we get to the point where we need to apply the chain rule to the second fundamental theorem of calculus. Now, let's go ahead and I hope that may not have answered everybody's questions about why, and that may not have answered any questions about why. But for the most part, that's going to have to do for right now. Let's go ahead and do a couple of extra problems that I found. I kind of poked around, but let's go ahead and start out a training wheels question. Okay, let's say we have g of x is equal to 3 to x of natural log t dt. Well, I know that if I was actually given the derivative of natural log t, that'd be fine. And if I was actually given the integral of 1 over x dx, I know that that's natural log of x plus c, right? I'm having a little bit of difficulty with the fact that the answer is not natural log, but the integrand is natural log. Again, one of those things that either A, can't be integrated, or B, with your current knowledge can't be integrated. We need to actually skip the step where we go to this implied difference over here and go straight to the derivative. And I know that basically the differentiation from g to g prime is going to undo that integral. But you need to remember that this was, even if you can't find the representation of g of x, a big G of x, and you can't find the representation or the value of big G of 3, you still know that those two exist. And basically, big G of x, or actually that's not G, that's F, but you get the idea. Basically, basically the antiderivative of this integrand right here. Even if you don't know what big F of x is, you know that the derivative of g is going to be back to f of x instead of f of t. It's going to be f of x minus 0. And that is, of course, what we have right here. Okay? Now, let's do one of the chain rule where we actually can plug it in, okay, and then differentiate to find it. Let's say I have g of x is equal from a, now let's actually do it to an actual number. Let's say 3 to x squared of 1 over 1 plus t squared dt. Now, this right here should look really familiar because that's the derivative of arctan, okay? If I have arctan of x, it's 1 over 1 plus x squared. So if this is a recognizable derivative, then to integrate that recognizable derivative gets me right back to arctan of t, and I'm evaluating it from 3 to x squared. So I get arctan of x squared minus arctan of 3. Okay? Now, this is still g of x. I haven't taken the derivative yet. All I've done is actually evaluate insofar as I can, actually do this integral and put it into its implied difference. Now that I've done that, I can go ahead and differentiate. Now I know that any time I have arctan of x, it's 1 over 1 plus x squared. But if I have arctan of u of x, which I do have here, that is not x, but a function of x, I have 1 plus u squared times du. And then, of course, the derivative of arctan of 3, since this is a constant, is 0. So my actual answer is 2x over 1 plus x to the 4th, which I could have gotten without doing this step right here, although I could in this particular case, because this was integrable, right, capable of taking the integral. It was integrable, so I could actually do this step, but as I've shown before, some you either can't do. There are some integrals that just can't be done by hand. You have to use your calculator or a computer to evaluate any definite integral, or ones that you can't do with the skill set that you have. Or how about ones that you could do with the skill set that you have, but you just don't want to, okay? So for all three of those scenarios, you could have, based upon the method that we talked about, the procedure, jumped straight from here to here, right? And gotten that very, very easily. Now, I keep running back to this implied difference because I do think, especially early on, it does help us to understand, especially on the chain rule questions, why exactly things are being done in that particular way, why the chain rule applies. Well, it's because in reality, you're not really taking the derivative of the integral, you're taking the derivative of the difference that is implied. And of course, since it goes from a constant to a variable or a variable expression, that first term is going to be the only one that you need to take a meaningful derivative of, because that second term is always going to be a constant. Okay. So this was probably a little more complicated than ones that we talked about yesterday when we had our session together. But I did wanna at least take a stab at answering the why questions that were broached, and I also wanted to go ahead and give you a few more examples. So between the session that we had yesterday, which I recorded, and please do let me know, send me a message if if something goes wrong with that and you can't access it. Between this video and of course the ones that I will point you to on the Virtual Fourth YouTube site, we ought to have a pretty good understanding, at the very least, of the procedures involved of straightforward second fundamental theorem of calculus, as well as the application of the chain rule to it. So I will look forward to seeing y'all on Friday, and I will answer any questions then. And from there, we will be venturing into 5.4, which is a section on the indefinite integral and the net change theorem. And after 5.4, Lord willing, if they have figured out how we're going to do assessments, we will test, okay, before moving on to the final section of Chapter 5 and into a couple of the applications for integration at the beginning of Chapter 6. But I guess that's it. I will talk to you all a little bit later. Bye-bye.